notational conventions. So like I will be telling you how a differential can be written, stochastic differential can be written in the form of integral. So you already know from differential equation all of these things as well. So like suppose if we have a differential written in the form of dxt, which is, so this is a stochastic differential. If some stochastic differential is written in this form, so I can put this same differential, stochastic differential, in the equivalent stochastic integral form by integrating on both sides. Let's say integrate it from a to t and write dxt to be equal to a to t f of t dw sub t dw sub t. Further we can write down, so like this turns out by the definition of, so like I should have put s over here just to make things look better. So this will be dx x sub t minus x sub a, which is equal to a to t f of s dw sub s dw sub s, and which can also be written as x sub t to be equal to x sub a plus stochastic integral or Ito integral of this function, right? So this is the equivalent integration formulation or the form of this stochastic differential, right? On the same lines, if we are writing this x sub t is written, let's say, in the form of x sub a plus a to t f of s dw sub s dw sub s, and you apply differential on both sides, and you can write dxt to be equal to the differential of a to t f of s dw sub s dw sub s dw sub, or you can even put it in this form, so like f of t w sub t dw sub t, which is dx sub t, right? So it is other way around. So like if you have something written in the integral, stochastic integral form, you can write it into stochastic differential form, and if we have something which is written in the stochastic differential form, we can write it into stochastic integral form in this way. So these are the notations, and of course suppose we have differential which is written in this form, so it is same, but like y of t dw sub t to be equal to f df sub t, so it is a stochastic differential. Then you can also write this stochastic differential in the form a to b y sub t dw sub t a to b df sub t, which can be written as f of b f sub b minus f sub a. So this is nothing, right? So we can write it in this form. So this is notational convention. Okay, so let me ask you a question. So let's say I have a function x and I want to integrate it with respect to dx, and let's say it is integrated from 0 to t. So the answer is basically x squared by 2 from 0 to t. So it is going to be t squared by 2 minus 0. So this is the integral of this guy, but this is not a stochastic integral, of course not a stochastic integral. But now my question is, on the same lines, if we compute 0 to t, the stochastic integral of Brownian with respect to Brownian, what answer should we expect? Should we expect this? And the surprising answer is no, we can't expect. There is something different. It looks a bit different from this. What is the difference? We can talk about that. So the next task of mine is going to be to calculate this crazy Ito integral. So for this, I will consider, so like I will be doing some sort of reverse engineering. So how I will be doing some reverse engineering. So you recall the Ito lemma, Ito lemma for Ito lemma for the function where my function is only depending on the Brownian, right? So Ito lemma for such function looks like this: 1/2 the second derivative dt and first derivative dw sub t. So this is how it looks like, the Ito lemma. So I want to calculate, okay, if I write it in the integral form, so my f is going to be look like f naught plus, let's say, 1/2 the integral of this guy plus f prime dw sub s, let's say. So it is, let's say, 0 to t, 0 to t. So if we compare this guy over here, this integral over here with this, so I need a function such that its derivative is equal to w sub s. If I'm successful in finding out a function whose derivative is w sub s, then that function, of course, the function is going to be this guy over here. So now I will do what? I will apply Ito lemma on this function. So first you compare this. So you need to find a function whose derivative is same as this. So like the derivative is this guy. So if you find such function which is this, in every case, whenever the integral is over here is only depending on Brownian, then you will find out a function whose derivative is equal to this function, and then you will apply Ito lemma on this function. So I will apply Ito lemma on this function. So for Ito lemma, I need to calculate its first derivative and its second derivative. So its first derivative is obvious, its second derivative is going to be 1. So then my Ito lemma says that df is equal to 1/2 f second derivative dt f first derivative dw sub t. So then d, and now my f is w squared by 2. So it is w sub t. So 1/2 second derivative is 1 dt plus this first derivative is w sub t dw sub t. So now if you apply integral on both sides, so then it is going to be okay, let's say my integral is from 0 to t. Okay, so like if it is 0 to t, then I need to change this variable into s. So this is like 0 to t, 0 to t. So this is going to be w sub t squared by 2 minus w sub 0 squared by 2 is equal to 1/2 0 to t ds plus 0 to t w sub s dw sub s, right? And then but we know that w of 0 or Brownian at 0 is 0, at time 0 is 0. So this is going to be w sub t squared by 2 is equal to 1/2 times t plus 0 to t w sub s dw sub s, right? So my task was to calculate this quantity, so then I can rearrange this to get 0 to t w sub s dw sub s is equal to w sub t squared by 2 minus 1/2 t. Now you see that when you compare this integral with this real integral x dx, so it was x squared by 2 from 0 to t, right? So like t squared by 2, which is same over here. Like if we compare 0 to t, let's say w sub s dw sub s, so one of the things that is going to be w sub s squared by 2, but there is something additional which is minus 1/2 of t. So this is something that is additional when we compare with the real real integral. So yeah, there is a difference in the stochastic integrals and the real integrals. So what technique did we apply? So we applied Ito lemma. So let me summarize what I said previously. So if I have a function which is depending on, so I will write this here. If I have a function g of w and I want to integrate this stochastically, so like it is in a stochastic integral whereby this function is only depending on w. In that case, you will do what? You will find a function f whose derivative is equal to g sub w. And if you are successful enough to find out such function, then you will apply on this function, you will apply your Ito lemma. So when you apply Ito lemma, then you will find its differential, the differential of f, and then you will integrate. And in that integral, you will have this quantity, which is GW, AW.